Okay, so in electrostatics, so what we did was a very basic fundamental introduction to electrostatics, and we saw the various methods of charging or to create charge bodies. The first was friction. By method of friction, we can create charge bodies. Second was method of conduction, and in conduction, what we saw that it is the difference of potential which allows the charge to go from one place to another place, and the whole idea is to make this process till the potential becomes equal, and when there is no potential the charge will stop getting transferred or will stop moving from one place to another place. So the potential concept was introduced as a qualitative way to, not qualitative, it's a quantitative way to understand the repulsion, right?
Yes, sir.
So it is the repulsion which matters. Okay. So when you connect two bodies with a different repulsion over the distribution of charge, they try to minimize the repulsion, and that is achieved by equating the potential, right?
Yes,
Okay.
sir.
So I think that was the last thing we studied was the quantization of charge, like how charge is quantized, and we can only create a charge on a body by transfer of electron, and because electron is having a specific amount of charge, which is 1.6 into 10 to the power minus 19 coulomb. So the charge which we produce on a body is always equals to the integral multiple of the E, and it could be plus, it could be minus, depending on how the transfer is taking place. So if you lose electron, it is positively charged, and if you gain electron, then it is negatively charged, right?
Yes, sir.
So this is what we did. Anything else that we did on that day? Probably no.
No, sir.
So now we can start with the very first law, the law which governs the interaction between the charged particles, or we say point-like charges. So there is a very famous Coulomb's law. I think the name was this Augustine Coulomb, and he was probably a French physicist and mathematician. And he gave or he in fact he got inspiration from the Newton's law of gravitation. And because, as I said, he found that the charge behavior is similar in terms of behavior of mass, with some differences definitely. And there is a law which governs the interaction of two charged particles or point-like charges. And this interaction is exactly inverse square law interaction, and which is similar to the gravitational interaction. So we can start with the Coulomb's law. So first of all, we need to understand that this law is a kind of a quantitative measurement of interaction. So it gives the quantitative, quantitative
Measurement of the interaction
yeah,
between charged bodies.
yeah, between charged particles. That's a very interesting difference that we need to understand. Measurement of interaction between two point-like charges. Now the sentence which we say point-like charges will have some bigger meaning here that we'll try to decode. Between two point-like charges, assuming if they are kept in vacuum, it follows inverse square law similar to Newton's law of gravitation. Okay. Now, this is the purpose of this Coulomb's law, what it does and how on what principle it is based on. So the formulation is very simple. So if I say that, let's say we have two point-like charges. Now I will explain what is point-like charges. So let's say we have two point-like charges, and generally we represent the charge by a symbol Q. Now there are two separate interpretation of Q. It could be a charge with sign, or it could be just a charge magnitude. So it is up to you to interpret. So I'm taking Q1 and Q2 as the respective magnitude of charges, and because both are positive, I have taken, so I can put a plus sign before. So Q1, Q2 only represent the value. Plus minus we can put it separately. In some scenario they don't put the sign, they just write Q1, then it could be plus also, it could be minus also, we don't know. So Q can be positive, Q can be negative. So these are two separate interpretation of writing. So we will keep the interpretation simple. We will assume Q1, Q2 as the value of charge, and if we want to mention the sign, whether it's positive or negative, we will explicitly mention in the problem, okay, or through the diagrams. So let's say we have two point-like charges which are at a separation r. So what Coulomb said that the force of interaction between these two point-like charges. Now, when I say force of interaction, then again I'm talking about the magnitude of force.
Okay.
Because again, it can have a different interpretation. It could be attraction, it could be repulsion. So when I say the word interaction, then I'm not differentiating between the two. It could be forming attraction, it could be repulsion. So that's why the word interaction takes care of both. So
Yes.
what Coulomb said, let me write it here. So what he said is simple, that force of interaction between two point-like charges assuming to be kept in vacuum. So we are believing that this law holds true, or this law will be the reality only if the two charges are in vacuum. If the two charges are kept in some medium, maybe air, maybe water, maybe kerosene, maybe some organic liquid, or any medium which is comprised of certain molecules, Coulomb's law and the reality will differ drastically We'll come to that later on, but we need to understand that the charge and the electric field are very sensitive to the the medium surrounding you. And why it is so? Because when I say medium, we talk about some molecule, some atoms, because what the medium is made of? Some molecule or atom, isn't it?
Yes, sir.
So even the air, which is a medium, is made of hydrogen, oxygen, nitrogen, carbon dioxide, and some other gases. So when I say medium, we talk about a large collection of molecules. And eventually we know that molecules are made of atoms, and we also know that every atom will have a nuclei which is positively charged and orbiting electrons which are negatively charged. So it is logical to understand that when you create a field, because every charge will create a field, the field will also interact with the charge which is present inside the atoms or molecules. So the interaction which will happen will not be just because of the charge, two charges which you keep, but due to the unseen charges which you don't see. Okay. So there is a infinite charge in the space in the medium which interact indirectly, and this indirect interaction we will also quantify in one way or the other. So we'll see methods which can take care of the the interaction with medium. So medium is an invisible collection of charge, and that is why the cosmic radiation is so powerful that it can excite the medium also, and it can create a lot of charge transfer, and these things are clearly visible if you go near the northern hemisphere or north pole of earth or the south pole of earth. So near the north pole you might have seen in Google or somewhere there is a phenomena called Aurora Australis and Aurora Borealis. These are
Yes,
like
sir.
called northern lights and southern lights, and these lights are nothing but the movement of charged particles which are generated from the medium itself, the air itself, due to the cosmic radiation reaching the earth. So atmosphere is preventing us, or in fact saving us from various high energy charged particles, because even a human body is made of atoms, and if something can interact with our atom, it can disintegrate atom into the medium, and so every individual will just vaporize into thin air, becoming, you can say, collection of atoms. It's so powerful.
Wow.
So there are various things which prevent us, and so the life on earth is possible because we have a very strong magnetic field around the entire earth, and these magnetic fields are the protectors of life on earth. So without these fields, what will happen is that we cannot prevent the cosmic radiation to reach the earth's surface. Once it will start coming in a bulk, the entire humanity will be destroyed. So this is one of the most striking reason why life sustains on earth, and that's very interesting that it is the magnetic field which is the protector of the life. So we'll see those things in a chapter of magnetism, how it does and how it prevents from getting destroyed. Still, the cosmic radiations are not completely stopped by them. So they enter to a great extent near the poles, and they produce a beautiful visual experience called the northern lights and southern lights, and one should witness in their lifetime if they can afford, right?
Yes, sir.
So now you can understand that how powerful is and how important is the concept of electric field. In fact, I can tell you that whatever you see right now is a complete electrostatic phenomenon. So vision is, if you go deeper into the picture of vision, vision is developed due to the electric field. So what exactly is vision is a very interesting topic. So what we call light is nothing but the oscillating electric and magnetic field, and later on you will come to know that light is an electromagnetic wave, and the electric field of light. So when you receive light, you receive electric field. Now that's interesting. And when this light enters your eye, so the pupil opens. So the human eye is like a window, right? So
Yes,
you
sir.
open the window, you let the light to get in, right? And when the light will get inside, what will happen? The light will get inside and it will hit the retina. Now again, retina is comprised of a very sensitive small cellular structure called the rods and cones. These are very tiny, very small in dimension. These are in nanometer dimension cell, and these cells having the ability to interact with electric field of light. And as a result of this interaction, these rods and cones are activated, or you can say they experience some force, so they start oscillating. And the oscillation of these cell structure creates a brain wave signal, and this signal passes, propagates through the optic nerve, and it reaches the part of the brain. And inside the brain, it reaches a particular point in the brain where we get the visual picture, and brain is able to decode it or map it into the beautiful uh, perspective. So whatever we see is the creation of brain, and we have taken it for granted. Okay, so that's why many times it happens. You might have heard that due to the brain injury, someone is losing the eyesight, someone is losing the ability to distinguish between the various color, because these are happening at a very small scale through various electrostatic interactions. In fact, human brain is the most powerful processor in the world. So we are so powerful processor, and then for your information, let me tell you that your brain consumes maximum energy from your body. So the more you process the brain, the more energy is consumed, because running a brain all the time is like running the engine all the time. Just like engine will consume the fuel, your brain will consume the. In fact, even if you're not driving the car, to keep the car switched on, you need to spend some energy, isn't it?
Yes, sir.
Similarly, even if you're not thinking much, your brain is doing some basic calculation, because every visual which you receive, every word which you listen, these all are information for the brain, and brain has to decode and process all this information. Some part is kept in the hard drive, and some part is kept in the cache. The cache is something which you can use as you want, but the hard drive requires some effort to fetch. So you can think that hard drive is like those information which are stored for a long time and not used by the brain. So you need to put some effort to recall and fetch. The process of recalling is having very special interpretation, and it leads to the development of uh, something called artificial neural network. So we try to mimic the way the brain behaves and how brain stores the information, how brain processes the information, how every single information which you either receive through the visual experience or through the acoustic experience or through some indirect touch or tangible or intangible experiences, everything gets processed. And what makes all this processing possible? At the core of everything, you will come to know it is the electric field. You can understand that how powerful is the concept of electric field. Also, you will come to know that in this chapter, I will teach you in the chapter of capacitor that human heart is nothing but a oscillating capacitor. So how heart knows that it has to shrink and expand, the pumping action of the heart to let the blood to flow through the various part. How all these things are achieved, at the core of all these things, what you will come to know is again electric field. And much more than that, even the life of a cell and the death of a cell at a microscopic level is again due to the creation of charge. There is a process called polarization, depolarization, and repolarization, which I will explain while teaching you the chapter capacitor. That even at a cell level, it is the charge which creates life. So the modern definition of life is that as long as the human cell is capable of undergoing this process called the polarization, depolarization, and repolarization, the life is present. And the moment this process stops, the life is over. Now, the heartbeat was earlier assumed as a process of life. So, if your heart is beating, you're alive, or else you're not alive. But the definition got revamped once we learned how to transplant the heart itself. So, you can imagine if a heart is transplanted, for some time there is no heart, isn't it?
Yes, sir.
So, you remove the heart and you make a connection. It means for some time there is no connection, isn't it? But still the human is alive, right? So the idea of this led to the change of definition of life. And if you have seen various Indian movies, you must have seen something like this graph in the ICU,
Yes, sir.
and these are nothing but the graph of time versus potential. So this is the potential and time graph that we'll learn later on, and this is the process of polarization, depolarization, and repolarization. So as long as this process is happening, we are alive. And if it is a flat line, it means the process has stopped. Body is not able to create this process. And then it is technically good to assume the person is dead. Maybe with some advanced knowledge of life, we may try to decode the life in a better way. And maybe we can create life even after 1 day or maybe after 1 hour to recreate the process, or maybe after 5 minutes. So I don't know the time duration, or maybe 1 minute. So a dead person can be brought to life by restarting the process, but we haven't achieved those technological advances which can recreate the process in the body naturally. So human brain is the engine which propels every function, and the rest are the mechanical parts. So human body is comprised of two things: one, the soul, which is the brain, and the rest are the mechanical devices. or you can say those devices which gets the instruction from the brain and behaves in certain way. So that's very fascinating for me, at least. The
Yes,
life having so many process, and everything can be understood very easily if you understand the concept of electric field. So now this chapter is the lifeline of various things. But of course, I mean, it is not that everyone knows in this way, the way we are trying to understand. So we are engineers, so engineers will always try to dig deeper into the cause of everything.
yes, sir.
Doctors
And
will,
now the
doctor,
concept itself seems
yeah,
so materialistic.
yeah,
It's like how a machine works.
exactly. So there is a, I mean, there is not much difference if you try to understand the functioning of a machine and the functioning of human body. You can find various similarities. Okay.
Yes, sir.
So what Coulomb said that if we have two charges Q1, Q2 kept at a separation, then the force of interaction is proportional to product of their magnitudes, and that's quite logical. But if you try to understand even more deeper, and okay, this is something which I also thought, why it is not the summation? Why the product? So now one reason is that this is the experimental thing, and that's true. But there may be some reason that the field, why it gets multiplied, because the interaction following some multiplicative, it's like scaling. So it's like if one charge can create something, the other charge can scale it. So where how we scale something? So if we have a value x to scale, we multiply with some number, right? And
Yes,
when you multiply with some number, it gets scaled. So if it is two, and if this is the vector, let's say if you know remember the vector chapter, if a vector, so this is the two-way vector, right?
yes, sir.
So just like a vector gets scaled if you multiply by some numbers, the whole idea of product is because the field gets scaled by presence of other charge. So this is the core of something which I mean no one has actually tried to understand. But even I thought for a while like why they multiply, why not they add or subtract. So of course experimentally we found its product is more relevant than the addition or subtraction or maybe division. But if you look carefully that the best way to understand is the scaling factor. So a charge gets scaled by another charge. So in a way, you can say that the ability to indulge in the interaction is getting scaled by the other charge. So this is like a scaling process,
Yes, sir.
and it is inversely proportional to square of the distance. So this is basically called inverse square law. This part is called inverse square law. So if we combine the two proportionality together, we can write something like this. And the inverse square law is something which Newton derived through his own observation. And how Newton came to this conclusion, because when the day Newton gave the Newton's law of gravitation, so he was working in the lab of, or you can say observatory of Sir Johannes Kepler. And the Kepler actually collected data from the various astronomical observation over his lifetime. And when the data was interpolated, because that time there was no computer, as you know, Newton was not born in the era of computer. So he did all these things manually, and then he was able to find the pattern in the data. And from there, he realized that, okay, this is following inverse square law. And later on, we realized that it is the inherent property of universe or the nature. The nature behaves by the inverse square law, or you can say the various interaction in nature naturally follows the inverse square law. So Coulomb was not something, I mean, Coulomb actually derived the inverse law through some experiment. In fact, I would say Coulomb was having this notion that it is going to follow the inverse square law, but he proved through very simple experiment. I'll show you the experiment that how Coulomb came to know about this inverse square law. So there was very nice simple experiment which he performed, and then he realized. So the force of interaction is proportional to product of magnitude of charges and inversely proportional to the square of the separation. And in physics, this is the proportionality means as Q will grow, force will grow, as R will shrink, force will grow. But the question is, what is the exact equality? So when you try to equate something and when you try to remove the proportional with equal sign, you need to put some constant, and this turns out to be this much. So Coulomb force is K Q Q2 by R square, and the value of K, of course, every proportionality constant will be determined using some basic experimental setup. So Coulomb performed a simple experiment, and when he tried to calculate the value of K turns out to be 9 into 10 to the power 9 Newton meter square upon Coulomb square. So that's the unit, and it is a close value. This is 8.98. So this is basically 8.98 10 power 9. But okay, for the sake of numerical calculation, it is good to assume 9 into 10 to the power 9, and that's totally okay. The unit is very easy to derive because it's, you can see it's Newton meter square, and this is Coulomb square, which will go here. So the unit is easy to understand: Newton meter square upon Coulomb square, right?
Yes, sir.
Now later on, for vacuum, so as I said, vacuum means there is no medium, so it's a lack of molecules. So no molecules, no atom, molecule, ions, or anything. So nothing is there. That's called vacuum. So in case of vacuum, the value of K was determined, and it is equals to 1 upon 4 pi epsilon naught. So this epsilon naught is epsilon, and we write naught NAUGST. This is how we write.
Yes, sir.
So I have given you the naught. This is epsilon naught, and it is called. This is a nice name. This is a Greek name. This is the name of the symbol, Greek symbol. And you know the word naughty, right? Naughty.
Yes, sir.
Naughty means someone who is dumb, knows nothing, right? So now you know the origin of the alphabet zero. So zero
Yes, sir.
means nothing. So someone who is naughty is like dumb, nothing. Okay, I mean that's a very bad correlation, but you can think this.
Yes, sir.
Okay. So this is called in chapter of electrostatics, this symbol having very specific name, and we call permittivity of free space. This is called permittivity of free space. Epsilon naught. Okay.
Okay.
So now we'll try to understand what exactly permittivity represents. So as I said in the beginning, every medium is made of atoms, molecules, or something. So when I say the medium, we do not understand there is a collective presence of large number of molecules and atoms. When I say medium, okay, so medium always means a collective presence of large number of, atoms, molecules, etc. And every medium will have some electromagnetic properties, because medium is made of atoms and atoms are made of charges. So medium will have inherent property, inherent electromagnetic property. Now this is something very profound, that although it looks neutral, but a medium is really powerful. It can affect things in various ways. So right now you're living in atmosphere. I mean, there is a air everywhere present. So you are already surrounded with one unique electromagnetic property containing surrounding. You can say this surrounding will have a unique electromagnetic behavior. So when I say that you go from one medium to another medium, then basically the very purpose of saying this is you go from medium with one property to another medium with a slightly different set of properties. So every medium naturally will have some electromagnetic properties, which is of course invisible. We cannot see. But medium without electromagnetic properties not possible. In fact, for your information, human body itself is a complete electromagnetic package. And right now, the potential on your body, the skin, if you have some oscilloscope and if you have some electrode connected to it, if you touch the electrode, you can see your body potential on the oscilloscope. So we have a potential of millivolt right now. It means human body is a charged body. Do you know this?
Awesome.
So we all are charged bodies, but our charge is not so strong. So we do not get affected by the electric field, because this is in millivolt. Okay.
Yes, sir.
So the electric field is everywhere. The body itself is a very powerful electric field. So permittivity, if we try to decode, let's determine the value of permittivity. So the value of epsilon naught, or permittivity of free space, the value is 8.85 into 10 to the power minus 12. And the unit is inverse of the k, because if you see this is the denominator, so it's inversely proportional. Coulomb square by 4 pi is the number which is a constant, and constants are dimensionless. So 4 pi is dimensionless, and dimension of k is known to us, Newton meter square upon Coulomb square. So we can say dimension of epsilon is, I mean, the unit is this much. So we can in fact find the dimension exactly. What is dimension of epsilon? So Coulomb is a charge, and later on we come to know that current is, you might have studied in class 10, charge upon time. So dimensionally charge is current in time, and current we measure in ampere, time in second. So the T is the symbol, I mean dimensional symbol for time. So we can write as A T square. Coulomb square is done. Newton is mass into acceleration. Force is mass into acceleration, and acceleration is meter per second square. Meter is L, and second square in the denominator we can add T minus 2. So this is the dimension of Newton, and meter is length square, right? And if you simplify this, what you can get is m minus 1 L cube minus 3. T will be how much? 4.
Yes,
And A
sir.
will be square. So this is the dimension of epsilon naught, or permittivity of free space. Okay.
Okay, sir.
So now, what is the significance of epsilon naught? We'll try to understand the significance. So if we substitute the k, we can write like this: 1 by 4 pi epsilon naught, and So this looks like a complete formula for the force between the charged particles. And F is equals to this much. And what else? This epsilon naught will have a significance. What is significance? If the bigger the value, is smaller the force because it is inversely, right?
Yes, sir.
So in a way, we can say when you keep two charged particles without any medium, then they interact in certain way. So this is the ability of the vacuum which determines how strongly the charge can interact. So what we say is permittivity. If you break down into two words, this is like permission plus resistivity. Now permission is to allow someone, and this is the to oppose, right?
Yes,
So
sir.
this two word you can, if you correlate, you can say epsilon naught is the inverse degree of permission, like you oppose the permission, right? So we say inverse degree of permission for the, permission of vacuum for the charges to interact. Understood?
Yes, sir.
So this is the inverse degree of permission for the, permission of vacuum for the charges to interact. So it's like how much vacuum is opposing the interaction between the charges. And why we are saying permission? It may look like that it's very counterintuitive that vacuum is doing nothing. No, it's in fact you will come to know later on if you do the higher studies that vacuum also having some resistance. So vacuum also creates some resistance, and that's why the force is not infinite. So it is having some finiteness value. So this epsilon naught is the measurement of that obstruction. It is of course allowing the charge to interact, and the obstruction is the least. In fact, you can say vacuum is something which offers the least opposition for the charge to interact compared to the medium. So the moment you enter the medium will be, it will bring a bigger opposition, and the moment we enter the medium, the force is bound to decrease. We'll come to know this very soon. So this is how we interpret the permittivity. Okay.
Okay, sir.
Permittivity is like, no, these are not bookish thing. This is something you, I have just decoded in my way. So the word makes some sense to me if I think this way. It's permission and resistivity. Okay.
Yes, sir.
So Coulomb's law is only this much. It's all about 2 point like charges, and but we have some limitation on the validity of Coulomb. Just something hanging. Okay. So limitation and validity. So what is the validity? First of all, this law is not applicable or not valid within the nucleus or dimension of nucleus. So within the, and why I'm saying so? Because if you remember, inside the nucleus we have similar charge like protons, and protons live together within the nucleus, right?
Yes, sir.
Every proton is a positively charged particle, so they should repel, isn't it?
Yes, sir.
But they live happily together inside. How it is possible? So the rule is simple. The nucleus is the mysterious place and no one knows much about it. Yeah, that's true. So within the nuclear dimension, I get confused. What is the spelling of Coulomb? CO?
Sir, I think Coulomb.
Let me just confirm. I'm just getting. Yeah, that's correct.
Yes, sir.
So within the nuclear dimension, Coulomb's law is not applicable. But as the separation will grow, as you go beyond the nucleus, the Coulomb's law will come into effect and repulsion will start. And that is why if a nucleus will have a bigger size, if you have a large size nucleus, so within this part, the Coulomb's law is not applicable. But as the size will grow, eventually Coulomb's law will start coming into picture. And this proton and this proton may repel each other because the Coulomb's law comes into picture suddenly. The distance becomes bigger. Coulomb's law will come, and that is the reason nucleus sometimes disintegrates. Okay, so this is also one of the reasons why nucleus gets, automatically they self-destruct themselves because of the Coulombic repulsion, and that happens for the large size nucleus, and this phenomena we call radioactivity. Okay, so the radioactivity is again basically a process of disintegration of nucleus and the emission of some particles which may be charged, which may not be charged, and this happens without any external simulation. So that's called the self destruction process. You can think this way. So it is spontaneous disintegration. The technical word is spontaneous. When I
Your
say the
voice
word
is cracked.
okay, just a minute.
No.
Okay, am I audible now?
Sir?
Am I audible?
Yes, sir. Now you're audible, sir.
Okay, is voice clear coming?
Yes, sir.
So what I'm saying is that the spontaneous disintegration of nucleus later on, the last chapter of this class 12 is called modern physics, and there is a chapter called nuclear physics. So in the nuclear physics, this is what we study, the radioactivity. Okay. So now this is one of the, you can say, cause behind the same, but of course this is not the only reason. May have many other reasons. This is one of the reason for this purpose. Okay.
Okay, sir.
So we cannot apply the Coulomb's law within the dimension of nucleus. Okay. So when it is not valid, so we cannot apply this for uh, non, because I mean point like charges. So if I give you a rod with some charge, and if there is a ball with some charge, we cannot apply Coulomb law in this case. So Coulomb's law and this charge is spherical ball. You're not supposed to apply the Coulomb's law, because the validity says that only for point-like charges. Now the time has come to explain what is point-like charges. Okay.
Yes.
Applicable only for point-like charges. Okay. So what is point-like? So let's say we have some charge here, and this is the separation. So the maximum dimension, this may be the dimension, the length, and here the maximum dimension may be something like this. I don't know exactly. This is maybe a magnetic maximum. And this is also dimension, the separation. So this is L1, this is L2, this is R. So imagine that these two charged bodies, which is of course not like a point, are kept at a very large separation. Now what does it mean? It means if R is much bigger than maximum of L1, L2, I mean this is just a mathematical way of writing. If R is bigger than anything else in the world, like anything, any charges which you are considering, if the separation is really large, then if the first charge will try to see the second charge, let's say you are standing here and your friend is standing here, but how your friend will appear to you? Like a point, like a dot.
Yes, sir.
And similar is the case for your friend and you. If your friend is looking at you, he or she will look at you as a point, as a dot, right?
Yes, sir.
So you will appear as a dot to, I mean, your friend, and your friend will appear dot to you, which means they are point-like charge. Okay. So point-like does not mean they should be exactly point. It only means that in a calculation, the R is such a dominating feature that their size is immaterial or negligible compared to the separation. And when this happens, you can treat both as a point-like charge and you're free to apply the Coulomb's law. Do you understand what I'm saying?
Yes, sir.
So if I say this is the separation of D, it is having a radius R, it is having the length L. If L and D, if L and R is, if L comma R is very, very small than D, you can apply Coulomb's law, not an issue. Okay.
Okay, sir.
Apply, else no. I'm writing in the reverse process. Yes. Anyway,
Yes.
this is not the right, so let's apply, else. So you can understand that the point, when I say point like, it is not actually point. It is a conceptual definition, and the definition says that in a calculation, when the separation is the dominating dimension compared to the individual dimension, then it is good to treat as only point like charges. And once you treat as point like charges, I mean, you're good to go with the Coulomb's law. definition. Okay.
Yes, sir.
Second, so this is, and Coulomb's law is the basically ability of one charge to either attract or repel the another charge. So when I say Coulomb's law, then I say it is the ability of one charge to attract or repel another charge, assuming if they are kept in vacuum. Okay. So Coulomb's law only talks about the ability, not the reality. Like Coulomb is saying that if you assume two charges are kept in vacuum, then they would have interacted with this magnitude of force. Now this is like, what how we say in, there is a grammatical term for this. So it's a future definite or something. Okay. So if this will happen, then that will happen. It's like uh,
So,
just a minute.
yes, sir.
Okay. So I think the concept of point like charge is clear. Hmm?
Yes, sir.
So what else we need to know? So now what I'll do is I'll bring some medium into the picture. So let me create a medium, and this is medium, and we have two charges Q1 and Q2. So now the medium will play a role, because the moment you bring a medium, and if you, let's say if you take two charge particle and you put inside a water kerosene, so let's say you dissolve some salt in water. So salt is basically sodium chloride, and sodium chloride is Na plus Cl minus are two ions, and these two ions in vacuum they strong. I mean, this is very interesting that Na plus and Cl minus are not at a zero separation; they are attracting each other at some separation R. This is the reality, and this R is
Yes,
called,
sir.
this R is called
Bond length.
bond length. So this is called ionic bond, right?
Yes, sir.
So now this is the in vacuum or in air. This is in vacuum or air. The moment you put the salt in water, the Coulomb's law will change. I mean, Coulomb's law will not change. I mean, I would say the force will change. So the way they held each other, because these are charged particles, so they follow Coulomb's law. Understood?
Yes, sir.
So for ionic bond is basically the Coulomb force of attraction. So because this is the Coulomb, they are bound by the Coulombic force, so they are very much prone to the medium. It means the moment you put inside the medium, the force will diminish drastically, and the diminishing of force will lead to the separation of ions, and this process is called dissolution. Understood?
Yes, sir.
So when you say that a salt gets dissolved in water, the process of dissolution is basically separation of ions from their respective molecules. And why this is happening? The answer is because ionic compounds follows Coulomb's law. So their bond is due to the Coulomb force, and because Coulomb force is prone to the medium, so the moment you enter the medium, the force will change.
Yes,
Now
sir.
the force between the charged particle we called not Coulomb, we call electrostatic force. We have a symbol Fe, and it's called electrostatic force. Understood? So
Yes, sir.
because this is electrostatic force, so now electrostatic force do not follow the Coulomb. Now, as I said, epsilon naught is the permittivity of vacuum, right? You see what I said? Vacuum of free space, you can say.
Yes, sir.
Every medium will have a different permission. So a medium will have its own permission. Okay, it will dictate the terms and condition of interaction. And why we have defined something like this? Because it is difficult. It is difficult to do the microscopic description of interaction between the charge and the medium. So in a way, we don't want to bring the calculation involving the medium. We want to keep the medium as just medium, and we are trying to hide the idea that medium itself is a collection of charge. Now this is the collection of neutral charge, because the medium will have equal amount of positive and negative charge, so medium is essentially neutral, but the neutrality is not at a microscopic level. Neutrality is at a bigger level, a level that we live in. Macro world will have the neutrality. At microscopic level, there is something called polarization, and this will come to know in a chapter of capacity. Okay. So
Okay, sir.
what we are trying to learn now is a different permission thing, and this is called permittivity of medium. And this symbol epsilon without the not sign, this is the permission that the medium will grant for the charge to interact. And there is a nice name to this. So the other name for this is called dielectric constant. And sometimes we also write as K. Now this K is nothing to do with the K of the Coulomb law constant, but we also use K for dielectric constant. Okay.
Yes, sir.
No, no, this is not this is not die. This is just no, this is this. So this is called permittivity of medium, and now we define something called epsilon r, which is the ratio of the permission of medium upon permission of vacuum. So this is called relative permittivity. And if you compare the permittivity of medium with vacuum, there is always a ratio, and this ratio is called, this is called dielectric constant. Understood?
Yes, sir.
So the epsilon r is epsilon upon epsilon naught, and therefore the epsilon is the product of the two. Okay.
Yes, sir.
So the electrostatic force is given by a formula which is similar to the Coulomb's law, but with a difference that the epsilon is replaced by epsilon, not is replaced by epsilon. So we remove the not by this symbol and then we write. Now, what is electrostatic force? This is the force which the charge will experience. So you can imagine the E for experience. So what you really feel about? So the moment you put some charge in a medium, they are going to feel this much force, and as the epsilon is generally bigger than epsilon naught, so the force is going to be, the actual experience is going to be much less than the Coulomb force. Understood?
Yes, sir.
What they would have applied in vacuum and what they would actually apply in, or actually feel in medium, different. Now Coulomb formula is fixed. Coulomb force is always this formula. So no matter in which medium you are present, if I ask you what is the Coulomb force, the answer is this. Why? Because Coulomb force is the ability. So imagine the situation, two friends are fighting. Okay. So the friend one will have some ability to punch the friend two. Okay.
Okay, sir.
Now there is a third common friend who goes in between to, stop the fight. So now what will happen? The first friend will blow punch to the friend number two, and two will blow some punch to the friend number one. But the third person will also receive a part of the blow. So the force experienced by the first friend or the second friend is going to be less than the ability, isn't it?
Yes, sir.
Because someone has come in between. So
Yes, sir.
you won't get the full punch. You get a punch with some resistance. Okay, that's why you get less punch. So the punch which you experience and the punch which was applied, is it same? No.
No, sir.
So what you experience is called electrostatic force, and what you apply is called Coulomb force. So Coulomb force is same everywhere because that is the ability. Ability never changes, but experience changes from one medium to another medium. So do you realize what I'm saying? The
Yes, sir.
electrostatic force is the reality, the experience, and Coulomb force is the idea. And therefore, when you solve question, you must apply the electrostatic force, not the Coulomb force. Now, in various situations, if the medium is air or vacuum, the two terms are to be same, right?
Yes, sir.
Because if there is no friend, then the punch will be exactly what you will apply. So, if the medium is absent, or if you are in air, air is as good as vacuum in terms of electromagnetic behavior. So you can say the electromagnetic behavior is not getting affected much by the air, although it is affecting up to certain extent, but not much. So the value of epsilon r is roughly 1 for air, and it is exactly 1 for vacuum. Understood?
Yes, sir.
And now we can come to the conclusion of Coulomb's law, that the force which the two charges will experience in a medium is 1 upon 4 pi epsilon Q1 Q2 by R, and this can be written in various ways: 1 by 4 pi epsilon naught epsilon R, which is the relative permittivity, and this relative permittivity is called dielectric constant. Okay.
Yes, sir.
So if you look carefully, then this we can also write as Coulomb force divided by dielectric constant, right?
Yes, sir.
And for air, since this is roughly equals to 1, so the electrostatic force is same as Coulomb force, right? Now you understand why this is the answer.
Yes, sir.
It is roughly same, and for a vacuum, it is exactly same. So now this will give us the idea that every medium will decrease the force, isn't it?
Yes, sir.
Every medium will decrease the force, and to your surprise, water is having the highest value. It is roughly 80. It's a number.
Oh,
You can imagine that the moment you add salt to water, the force between the sodium ion and the chloride ion decreases by 80 times. It's so weak, and
yes,
that
sir.
is the reason they get dissolved easily. So now you know why water is such a good solvent, because of such a high value of dielectric constant, 80. That's too much. So if the force will decrease by 80 times, then the hydronium ion, which is H3O plus, which is the H3 aqua, right? So it means, sorry, H plus, whatever. H plus. So H plus do not exist in water. It exists as
Hydronium ion.
hydronium ion. Okay, if you have studied chemistry, you might be knowing this, right?
Yes, sir.
So the because H3O plus, the hydronium ion is also ion. So generally, what happens? The sodium ion, they lose their strength of attraction, and these gets attracted to the various components.
Yes, sir.
And
Sir,
that is
so ions tend to be an effective barrier as compared to atoms, sir, while diminishing the force.
right, definitely. So that's why the water is a good solvent for the ionic salts, because they follow the Coulomb's law, but organic compounds cannot be dissolved because they don't follow it. So the
Yes, sir.
law of interaction is different there. That's why they do not get affected by the water or a medium. Okay. So
Okay, sir.
medium can only affect the Coulombic interactions, not the non-Coulombic interactions. So we may have something called van der Waals forces, and we have some weak forces. We have something called maybe dipole-dipole interaction. So we have many various things. Okay. So the whole idea of, the chemical reaction, it has to do with the medium a lot. So now you know that why water is called universal solvent, because water is the medium with highest dielectric constant. Okay.
Yes, sir.
Hmm. So what does it mean? That is, the moment you keep the charge in a medium, the force will be less by this factor called dielectric constant. So I can say that some force is applied by the medium, right? So what is the force that medium applied? So I can say the
Sir,
force that medium
F
applied is
minus FC by ER.
correct. So
Okay.
this is, yeah, that's correct. FC1 minus 1 by. Okay.
Yes, sir.
So now you know that medium is capable of applying a force, and this force depends on the value of dielectric constant. And what is this representing? This represents the electromagnetic. No, this is not BMO. This will absolutely not represents. So this is a factor only. This is some number, dimensionless one. This is the dimensionless one. Okay.
Yes, sir.
So later on, we will come to know that this leads to the, and of course, it is in a way, it is a representation of electromagnetic behavior. That's true. And later on, the epsilon r will become the base of something which you call refractive index of a medium. So refractive index is a function of this.
Okay, sir.
I will explain, but this is not a function of this. This is also a function of this. So refractive index of a medium depends on the electrical and magnetic properties. So electromagnetic behavior, because it's a complex thing for us, so we have formulated a simplified version of it, and we call it refractive index, and we assign some numerical value which is obtained through the rigorous calculation. So you may be knowing the answer for water is, well, let's say 1.33. For glass, it is roughly 1.5. In various cases, 1.4 to 1.56. We have filled glass, we have crown glass, and so many things. But if you go deeper into all this, it is obtained by the electromagnetic interaction. So there is a rigorous derivation which we can only study if we do masters in this. So you can imagine that these refractive index are again derived from the laws of electrostatics and some, of course, use of mechanics. Okay.
Okay,
And
sir.
why it is so? Because as I said, light is an electromagnetic wave, and that's why a medium with electric property and the light with electric behavior, they can interact. Not a big deal, isn't it?
Yes, sir.
And because of this interaction, light is able to bend itself. Okay. So the role of medium is to bend the light. Okay.
Yes, sir.
And bending is the only thing that the medium does, and through the calculated bending of light, we achieve something called magnification. Okay. So whether you talk about the glasses, mirrors, lenses, or whatever slab, these all are medium eventually, and by giving different shape to the medium, we name it differently. That's like fancy name. You call convex, concave, and you say glass slab, you say mirrors, you say lenses. But what is all this at the end? It's just a medium with some shape, and the shape will allow some bending to occur in a different way. So by giving some distinct shape, we get some distinct bending properties, and that's why we study the chapter of light. So now imagine that the whole ray optics is a study about bending of light. That's it.
Yes, sir.
And if you look closely, the lens is nothing but a medium with a shape. That's it. So what is the whole idea of learning the ray optics? To understand the bending. That's it.
Yes, sir.
And when you see the light is bending and coming to a point, you call it focus. That's your problem. Okay. So
Yes, sir.
now you know what is focus. Focus is not exactly anything real. It's just like once you bend the light, where you see them coming together. So you call it, okay, if I bend the light, and if the light is paraxial, very close to the axis, then it appears to be coming at a point. At that point, I will prefer to say focus. That's it. So the entire bending, how light bends, even if you try to understand how the light bends, it is because of the electric phenomena. Now let me show you. I mean, this is something very deep. I mean, you won't get in a book, but I will teach you like how you can imagine. So
Yes, sir.
imagine an electric field having two components, okay? Ex and Ey. All right. So what is the actual direction of electric field? Like this.
Yes, sir.
Now, what happens in reality, in the real world? Because of the medium, one of the component gets disturbed. So it may get elongated or may get reduced. And once you reduce one of the component or elongate it, the resultant field will change.
Yes, sir.
Let me show by different colors. It may change like this, or it may change like this if it is really big. Exactly, this phenomenon is called bending of light. You change the direction of electric field. Understood?
So
Hmm.
due to the
And
difference, I mean, like
yeah,
when they
component. Yes, yes,
interact,
exactly.
they will be
Yes,
creating like a new
yeah,
vector.
yes, 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 exactly. So in reality, it is the interaction of a electric field vector of light with medium, which leads to the distortion of the component, and as a result, the light will now propagate in a new direction. Okay, and that
Okay.
is so interesting, isn't it? Like, I mean, it's fascinating. I mean, oh my God, this is the result.
Yes, sir.
So everything is related to the charge and the electric field, and that's why this entire thing is so related that if you understand one thing better, you have a better vision to see other chapters in correlation to the first chapter. Okay.
Yes, sir.
All right. Now, of course, the previous page, these are not the accurate description, but you can get the sense of it, why it is happening. So it is some sort of description which we need to know. Not this is not the complete description, but it is of course a part of the description. Okay.
Yes, sir.
Hmm. So we'll see in the sector of light. I will teach you light sector, and you will realize that light is such a fun chapter. I mean, it's easy and just a matter of geometry because you change the shape and you get a different answer. So the moment you start understand the basic of it, you realize that okay, this is nothing, just time pass. All these chapters are just time pass. Okay, so coming to the Coulomb's law, we have three things to highlight here. FC, highlight like this. FC, um, FE, F, and the formula is 1 by. So when I write K, I mean this one. Okay, so K is this. In other case, we cannot write K because that will be confusing. So
Yes.
here the formula is 1 by 4 pi, and this formula is 1 by 4 pi epsilon naught into dielectric constant into Q1 Q2 by R square. And this formula is the difference of the bunch minus exponents. And the medium will actually. So let me give you a small, like a visual sense of it, why it happens. So you can remember with ease. So we have two charged particles. So So now try to understand this. This is not required. So what is medium? A medium is a collection of atoms, right?
Yes, sir.
So what happens if you imagine the atoms near this charge? There is a process of induction. If you have studied the induction, so it will pull the negative charge of the medium close to itself, right?
Yes, sir.
It will happen on both sides, and this will pull the negative as well. So now what will happen is this charge will experience two forces. One, the Coulomb force towards left,
Yes, sir.
but this is the Coulomb force. Like both will repel each other, isn't it? Both will repel each other.
Yes, sir.
So assuming that, okay, for the time being, I'm assuming that let's say medium is doing nothing to the charge. Let's say medium is having no electrical property. Hypothetical. For the some time assume. If this is so, then the medium will not affect the answer to Coulomb, isn't it?
Yes, sir.
So they should have applied the formula which we wrote earlier for the Coulomb's law. But what is happening? The induction process is creating another charge which is opposite, and this is going to attract, right?
Yes, sir.
So every charge, the net force that you will experience is how much? Can you see that?
Sir,
Yeah.
like how is the like what is influencing the electrons to come like to one side again, sir?
So imagine we have some molecule here. I mean, again, we need to go even deeper. So we have an atom here, but because of the charge, this will become like a oval shape, and the negative will be pulled towards left, and the positive will be on the right side because of the attraction. Now this will happen, of course, from every side.
Okay, sir.
But it will also happen from this side also. But this is not. I haven't shown here. But the density will be more on this side and less on this side. Okay. And why the density will be more? Because the electric fields coming from both the charges will, okay, that will come to know later on. So imagine that, okay, this is true, because when I will teach you the chapter, I mean, the topic of electric field lines, you will realize that why it is more on the one side and less on the other side. Now this interaction will make sure that we have greater presence of negative charge on the right side and less on the left side. And these are the medium molecules. So although molecules are neutral, but in the presence of field, they get distorted actually. And the distortion creates the
Presence
oval
of
shape. Yeah, it's
yes.
called the separation of charge. This process is called polarization. So we polarize the molecule. Now polarization simply means you separate the plus with from minus.
Yes, sir.
This polarization is the cause behind the interaction of medium with the actual charge. And this interaction lead to the change of the force which you actually experience. Okay.
Okay, sir.
But it is because the medium is doing something, so we blame, in a way we put the blame to the medium. See, Coulomb force is not getting disturbed, no? Coulomb force is same.
Yes, sir. We just add an opposing component.
Yeah. So we see what Coulomb is doing is still the same thing it is doing here also. It is the medium which is changing the net value, and that's why the experience will change. So that's why I told you that if I ask you that if two charges are kept in a medium, then the Coulomb force will change or remain same.
So Coulomb force will remain same.
So what will change is the net force, right?
Yes, sir.
So the net force is called electrostatic force. Understood? This is the
Yes, sir.
net. And in the absence of medium, can we say the net force is same as the Coulomb force? That's logical. Hmm?
Yes, sir.
Okay. So is the difference between the Coulomb electrostatic and medium is clear?
Yes, sir.
Very good. So now because we have learned one formula, so we are now in a good position to solve some numerical question. Okay.
Okay. Yes, sir.
So the first question is, we have two charges. Okay, one more thing I need to mention about Coulomb force. I totally missed here. Okay, so just let me just cover this part. Okay. So one more thing which I need to mention here is spherical charge distribution. So for charge distribution with spherical symmetry, it can be treated as point-like charge, assuming all charge to be kept at the center. Of now, this is very, very important. Now, if we have a spherical charge, but not a sphere, I'm saying there's a difference in the spherical body and spherical charge. So what I'm saying is, if we have a spherical, I mean a charge which is spherically distributed, it means if you look in 3D space, the charge is spread spherically and symmetrically everywhere. Understand? Then you can treat the entire charge on the sphere to be kept here. So you can imagine that this is at the center. Okay. So this is as good as charge at the center. This is Q, this is, and then you can apply the Coulomb's law. But the charge should be spherically symmetrical, not the body. Hmm. Just let me have some water.
Yes, sir. Hello, sir.
Okay. So in case of spherical charge distribution, not charge, and not like what is spherical charge distribution means, if you look at the charge, it will look, if you look at every layer of it, it will be a part of a sphere. Okay, and it should be symmetrical as well, which means the distribution should be similar in all directions. Okay,
Yes, sir.
then we call it spherical symmetricity, and if it is not, then we don't see. So let's solve some numericals. So imagine we have two point charges and the distance is 1 meter. So we have two charge bodies, two charged particles are kept at a separation of 1 meter. Okay. Now you know what is the question? Question is, what could be the minimum value of, what will be the minimum force between charges? Force between the charge. Next question.
Sir, like the maximum force would be like if these two charges are kept in
Minimum.
the, sir?
Minimum. Yeah, you see, it is already in vacuum. So by default, when I don't mention anything, you can assume vacuum. So vacuum is there.
Okay.
Now, what is the minimum possible? Like that is a tricky question, but you can think about it.
Sir, so we are assuming that these two charges are kept in vacuum.
Yeah. That is already there.
Um,
See, the
Sir,
hint is,
if we assume if we assume these two particles to be like having very low charge, then
yeah,
wouldn't that be like the minimum
yeah,
threshold?
correct. Yes. So what is the minimum possible charge? That's the question. What is the minimum charge you can develop on a body?
Sir, wouldn't it like tend to 0 then?
10?
Sir, wouldn't like then the force between them like tend to 0?
Yeah, tends to 0. Is it possible to have, because these are charged bodies, so what is the minimum possible charge you can develop? That's a trick part.
Oh, yes, sir.
Got it.
Yes, sir. Quantization.
Correct. So the minimum charge you can think is 1 electron.
Yes, sir.
So both must have E and E, because we cannot have charge less than this value. So the minimum force is K Q1 Q2 by R square. That's simple.
Yes, sir.
9 into 10 power 9 into 1.6 10 power minus 19 whole square to mathematics. That's it. So this is just a tricky question, and what I'll suggest you that just to get some, it's like freeing your mindset to solve question like this. Open a book of S.C. Verma. If I hope you have S.C. Verma.
Yes, sir.
So it's a volume 2. So volume 2 of S.C. Verma, and yeah, are you ready with the book?
Sir, yes, sir. I'm searching for it. Sir.
Okay. If you don't have, then let me know. I'll just send you the pick of the questions. If you have, it's good.
Okay, sir. Sir, just a second. Sir, which chapter, sir?
Yeah, electric field.
Okay, sir. Yes, sir. I opened it, sir.
So now what you can do, you can try the first 12 questions or 13 questions. Okay. So
Oh,
meanwhile, you can try this question. I can take a break and I'll have my dinner and then I'll come back. Okay. So we'll
okay.
continue the lecture after some time also. I will continue lecture late till maybe up to 11 o'clock or as much as possible. And I'll just take a short break of 5 to 10 minutes and I'll be back. Okay. So you can try
Okay,
these
sir.
questions.
Sir, first 12 questions were, sir.
Yeah, first is done. So you can just do the question which we haven't done. Okay.
Sir, is it like in solved questions or in the exercises? Sir?
Just solve in rough. You can solve and you can get the answer.
Okay,
1
sir.
to 12. 1 to 12. Okay. 1 to 13. 1 to 13. All right.
Yes, sir.
Yeah, are you saying something?
Sir, no, sir.
Okay.
Sir, can you just tell the page number?
Hello, Sika, how many are you done?
Sir, I am in the sixth question, sir.
Very good.
Sir.
Okay, you can continue. Because this just needs some practice, because once you have the habit of using the formula again and again, then you will find very much comfortable with this entire chapter.
Okay, sir.
So do it till 10, then I'll start the other part. So, then the rest I can leave. You can leave and then you can do it as a homework. So solve at least up to 10. Okay.
Okay, sir. Sir?
Yeah, tell me.
Sir, I keep getting error in the sixth question, sir.
Let me see. Let me see. Just now. Sixth question. So two charges are placed at a separation this. So where should third? Ah. Okay. So the third charge you can put in between somewhere. And okay, leave this question. Okay. Okay. Let me teach you. I mean, leave this.
Sir, like, can you just tell like if I'm approaching this the right way, sir?
Yeah. Tell me.
Sir, I like these are like Q. I assume these charges to be Q and 2Q, since like it's a
Yeah.
factor of 1 into
Right.
10 power minus 6.
Correct.
And
And
then
assume the third charge. Yeah. Yeah. That's
yes,
good.
sir.
And you can name it, let's say Q naught, some just name it by some name, and you can say this is X, this is uh, D minus X. Let's call it D minus X. So this
Sir,
is at rest. This is at rest, no? The middle one.
yes, sir.
So which means the net force is 0. So this will repel this way, and the right will repel left, and we have to balance the forces. Okay.
Yes, sir. Sir, then here it will be like 1 by x square is equal to 2 by d minus x whole square, right, sir?
Correct. Exactly.
So if I solve this question, if I solve this equation, I'm not getting the answer, sir.
No, that's very easy. No? So you have to just take the square root. Don't take the don't expand it.
Oh, yes, sir.
This is pretty easy now.
Yes, sir.
You should have written this way.
Yes, sir.
Okay, so let me solve a variety of problems from this chapter one by one. So what I'll do is I'll first solve some even more conceptual problems. Okay, so imagine we have two spherical charges. So when I say spherical charge, it means the distance should be taken from their center. So and let's say D is the separation between the center. We don't take anywhere else, we take center. So now let's say I give some charge here and I give some charge, but it is not mentioned that how much. But what is given is that the total sum of charge, if you add this and this charge, it turns out to be Q. So out of Q charge, some is given to the first sphere, some is given to the second sphere. And so the obvious question is, if the total sum of charge on both spheres is Q, then what is the maximum force possible between the, so you understood the question?
Yes, sir.
What is given is the sum. So if I assume Q1 on the first, Q2 on the second, so Q1 plus Q2 is Q, that is given. So I want to know that how we must distribute the charge, total charge Q, in order to maximize the force.
Okay.
Okay, so try this. This is very easy and interesting. We have done this in basic math.
Yes, sir. Sir, when it's like equally distributed, sir, Q by 2.
Correct. Very good. So this is pretty simple. If I say, this is very interesting. This is if I write k x into q minus x upon d square. So we have to basically maximize this proportion, and this is a pretty easy and known value. So there are various ways you can write. You can say it's a quadratic, so minus b by 2. You can say it's a a function of x, so we can differentiate and equate to 0 as well, right?
Yes, sir.
So if you differentiate, we get x minus 2x, q minus 2x. And this is a formal proof. So df by dx we have to equal to 0, and this will give us this answer. So that's all.
Yes, sir.
So now this is interesting program based on conduction. Question is three identical conducting sphere. So three identical conducting spheres. So how is that? Imagine it's identical even if there is some difference in representation. So the first, so initially the first and third are neutral, only the charge is given to the middle one. And their separation between the first and the third is, let's say, d. So there are sequence of steps that we follow. So sphere 2 touches 1. Sphere 2 touches 3. Sphere 2 is removed. Find force between 1 and 3. After this sequence of steps, now what will be the force? Of course, Coulomb force. If nothing is mentioned, vacuum or air is assumed. So do this.
Sir, so like when 2 touches 1, the charge will be equally distributed till their charges
Correct.
match.
Yeah. So the final will be how much? The final charge here will be
Q by 4.
what?
Sir,
When is it?
sir, like 1. Okay, the second one is 2. Sir,
Yeah.
I was like
Yeah.
when
Understood.
again this after the second contact.
Yeah. So it means the third will have.
So Q by 4.
Correct. This is easy now. This answer is K Q square by 8 D square. That's it. Okay. So this is not difficult. Uh, let's do some conceptual question. Like what? Mhm. So there is a big sphere, and what we do is we remove a spherical portion. So the total charge is, I mean, only on the white part. The black is like a part which is removed, and the radius is r by 2, and the radius of the bigger sphere is, and we have a point charge kept here. And the separation between these two center is let's say D. So this is a special one because here we do not have the spherical charge, right? We have a sphere with cavity. Although cavity is also spherical, right?
Yes, sir.
So the way of doing this problem is that you first assume the cavity is present, which means we have a complete sphere. And as I said that in case of a sphere, we are supposed to assume as a point like charge, and all charge we can assume at center. Hmm?
Yes, sir.
So first we are find the force assuming everything is present, nothing is, there is no cavity at all, we get the answer. In the next step, what we do is we assume again a sphere, but only of the size of cavity.
Sir,
And then
what
again,
about the charge, sir?
no, you will apply the Coulomb's law between the two charges. You have to write K, Q, and Q2 by R square. But you have to write in two ways. First, you will assume full sphere and the charge Q. Okay.
Oh,
Step one. Step two, a small sphere exactly of same size as cavity kept in the same cavity location, and again this charge. And you can see that if only cavity part is considered, the force would be like this. And if
Yes.
the total is considered, the force will be a bigger value. So the answer to this question will be the cavity contribution we must subtract. Okay. So the actual force will be if assuming complete sphere minus if assuming sphere only in cavity. Are getting my point? What I'm trying to convey here. This is like the part which is missing will have some contribution, and if I subtract that contribution from the total, what I'll get is due to the remaining part.
Oh.
Do you understand a bit? It's difficult, I know.
Sir, like just the sphere mass is filled, or we add, or are we like adding some like more charge to that cavity part that is being filled? Sir.
Correct. So you have to fill with the charge similar to the charge density of the big sphere. So
Oh,
what we will define is charge density rho hypothetically, and we can say q upon 4/3 pi r cube. So this is the actual charge, right?
yes, sir.
And after the, so what we'll do is we, in the first case, we'll let q initial equals to, q in the first case will be equals to, just this one is hanging. Just okay. So in the beginning, don't write this formula. You just write q rho into 4/3 pi r cube. This is the answer, right? And the charge in the cavity is how much?
Sir, the corresponding density into that volume, sir, cavity volume.
Correct. So you can use the charge formula. So what you have to write is, let me tell you what you have to write. Kq total into q by d square minus kq cavity upon, now this, there's a trick here. So this will be d minus r by 2. Why? Because the distance from the center of the cavity and the charge is not d, right?
Yes, sir.
This is d minus r by 2, right?
Yes, sir.
So this is the formula. I mean, if once you write everything and you once you substitute everything, so yeah, you can get the answer. Is this clear?
Okay, sir.
Yeah, it's difficult. It's not easy, but you can do the calculation at home. I'm leaving the calculation part. Okay.
Yes, sir.
So now there are a lot many more questions, but what I'll do is I'll introduce those questions. I mean, after some theory. So look at this question. Uh, some realistic questions. So we have two conducting spheres at close separation.
Sir, can you just come back in a minute, sir?
Yeah.
Sir, can you just change the change to another device, sir? My sis needs my laptop.
Okay, okay, no problem. You can change.
Okay, sir. I'll be back in 2 minutes, sir.
Yeah.
So sir, are you able to hear me? Hello, sir.
Metallic sphere. So let's say you give some charge. You give some charge. Now, first of all, metals are something which keeps the charge on its surface, and because of the repulsion between the charge will be moved away from each other. In a way, the back of the sphere will have bigger density than the front. Why? Because of the repulsion. That's obvious. So you can
Okay,
see
sir.
that although the charge is on the sphere, but is the charge spherically symmetrical?
No, sir.
Exactly. So now the spherical symmetricity is disturbed. Can we apply the Coulomb's law?
No, sir.
No, we cannot apply. But we can say something that if it were symmetrical, the force would have been how much? Q1 Q2 by d square, assuming if it is symmetrical.
Yes,
Now
sir.
my question is the actual force. If I say Fe, can we say something about these two forces is more than, less than, equal? What do you think?
Sir, it would be less.
So if I say, even if I say just F, let's say F. So the F will be now less than this value. Why? Because the effectively the charge has moved away from each other, right?
Yes, sir. Sir, is there a delay in my voice?
No. I mean, it's coming now perfectly.
Okay,
So what
sir.
will happen is the charge, if symmetrical, the center of charge must be at the center of the sphere, right?
Yes, sir.
Because of this lateral shift on the left side, can we say the center of charge has shifted slightly leftward?
Yes, sir.
So there is a concept of a center of charge, and there is a similar concept here of center of charge, and the center of charge behave exactly similar as center of mass. So what we are going to define here is effective separation, and we can say that although Coulomb force we cannot apply, but we can say one thing for sure that the effective separation has increased, which will lower the value of F. So F is going to be less than this value. Now, if we ask a similar question with one small change, what is that change? So if I give one sphere plus Q1 and other is minus Q2 in a similar setup, what you can say about the new force? So
Sir, it would have increased the attraction.
yeah, correct. Because it will come even closer to the actual value.
Yes, sir.
So here, because of the attraction, the center of charge will shift forward. So it will be somewhere like here and somewhere here. And therefore the effective separation will decrease. If I say this is a D, the effective in this case will be less than D, right?
Yes, sir.
And the plus will be coming this side more than the back, and minus will be coming more on this side than the back. And therefore, the force which they will experience is more than. So these are some conceptual questions in which the once you disturb the symmetricity, you cannot apply the Coulomb's law for sure, but you can infer some inequality or inequality relation. You can say this is what we can do. Okay.
Okay, sir.
So these were the some conceptual questions that we should know, and next lecture will be more mathematically involved because we are going to learn the vector form of Coulomb's law. And after the learning the vector form of Coulomb Force, we can explore a large variety of problems. Okay. So the next two lectures
Okay,
will
sir.
be only numerically based problems. Okay.
Yes, sir.
All right. So with this, we can end today's lecture. And
Okay, sir.
tell me when you're free next. I mean, next today is Monday, no?
Yes, sir.
Today is Monday. So Monday, then can we keep on Wednesday? Or
Okay, sir.
do you have some lecture on Wednesday?
Sir, I also have a max lecture on Wednesday, sir.
Okay, so we'll keep on Thursday as usual, and then we'll keep one more either on Saturday or Sunday. So you let me know.
Yes, sir. Sir, this month you told like there'll be like 3 to 4 classes per week, right,
Yeah,
sir?
yeah. Yes, yes, correct. That's why I'm saying Tuesday, Thursday, and maybe Friday or Saturday, any one day. And each lecture we'll keep lecture of 3 hours duration.
Okay, sir.
Like,
Sir,
yeah, tell me.
sir, on Friday and Saturday, will you be able to take morning lectures, sir?
Yeah, no problem. But morning, how morning? Like Indian time, I can take around 8 o'clock. Is okay.
Sir, okay, sir. Here it's 6:30. Yes, sir.
So what time is suitable? Like 10 o'clock?
Sir, anytime, sir, in the morning.
All right. So I'll let you know. Yeah, I'll let you know. Morning means not strictly before 12. I mean, like before 12, or it can go up to like 1 o'clock up to. That's fine.
Yes, sir. I mean, like on Fridays and on Fridays, I'll be having like a class, Abhishek sir's class in the evening only, sir. And on Saturday, I don't have any class, sir.
So if I keep on Friday, then in the morning. If it is Saturday, then I'll keep on the morning on. So I'll keep in morning anyway.
Okay, sir. Yes, sir.
Okay. So I'll let you know. Today was the first lecture, so even I'm tired. So it's just like I'm again beginning after 1 week. So today I'll end lecture here because this is conclusive end, and then we start from next lecture. Okay.
Okay, sir.
And just let me know which date PPT I have to send. I'll send right away.
Yes, sir. Okay, sir.
Okay. Bye and take care.
Bye, sir. Thank you, sir.